I am Dr. Revathi, Associate Professor in Physics from H&S Department, Mlritm, Hyderabad. Today we are going to discuss about the Einstein coefficient derivation, continues to our previous class. We are going to learn about what are Einstein coefficient and derivation about the Einstein coefficients. So first of all, we need to know what are Einstein coefficients. So as we know that we have three types of quantum processes. One is stimulated absorption, spontaneous emission and stimulated emission. So based on these three processes, we are going to derive a relation. That relation we are going to call as an Einstein relation. So how we are going to derive? We can see step by step. Okay. So at first we need to remember the three processes. One is the absorption. So let us see this diagram. So you see here, where E1 is the energy of the ground state and E2 is the energy of the excited state. In the same way, if you observe here, where N1 is the number of atoms in the ground state and N2 is the number of atoms in the excited state. Okay. In first process, so what is going to be happen? All the atoms are in the ground state. So for this atoms, we are giving some energy. So that energy we are called as a photon energy. This energy is difference between the E1 and E2. This energy is difference between the E1 and E2. That means we are incidenting some photon energy. That photon energy is equal to E2 minus E1. So if you incident some energy to the atoms in the ground state, so the atoms absorbs this energy. Which atoms? The atoms in the ground state absorb this energy and they started to move from ground state to the excited state. So this is absorption process. So here we can see what is the Einstein coefficient for this absorption process. Here we can say with the help of these three processes, we are going to determine the probability value. In previous class, we say that this quantum processes means it is going to have the dual nature. One is the quantized energy levels, first one in quantum mechanical, and second one is the dual nature. Dual nature means here the particle nature and the wave nature together. Here our light is that means our photon energy is the wave nature and our atoms are the particle nature. Both together we are going to call as quantum processes. So let us go with this Einstein coefficients one by one. So here first if you see, where N1 is the number of atoms per unit volume with an energy of E1. Where N1 is the number of atoms per unit volume with energy of E1. That means N1 is the number of atoms and it is having the energy of the E1 in ground state. In the same way, where N2 is the number of atoms per unit volume with energy E2. That means N2 means the number of atoms in excited state with an energy value of the E2. So here we have, for these three processes, we have two main transitions. One is upward transition and second one is the downward transition. First, this absorption process is involved in upward transition. That means the atom is moving from ground state to the excited state. That's why we are calling this as upward transitions and downward transitions. So let's see that. And this incident energy, this photon energy, we are going to call as energy density. So this photon energy we are going to call as energy density. So this energy density we are going to represent rho nu. This photon energy we are going to call as energy density. So let's start this derivation. So here we are going to say that, so the ground level we are going to call as level 1 and the excited level we are going to call as level 2. So here what is going to happen? So in stimulated absorption process, the transition rate is going to be depends upon the how the transition rate is going to depends upon means the transition rate is going to depends upon the number of atoms in ground state and the incident photon energy. So that means, so from 1 to 2 transition process, the rate of absorption is going to going to proportional to number of atoms in ground state and the incident energy. So if you see here, so the stimulated absorption forces is going to proportional to number of atoms N1 and energy density. So that means if you write R1, where R1 is the rate of stimulated absorption, where R1 is the rate of the stimulated absorption. The stimulated absorption is going to proportional to number of atoms in ground state, and it also depends upon the energy density. So if you take off this proportionality constant, we are going to get some constant. So that constant we are going to write B1 to N1 rho nu. So N1 is the number of atoms in ground state, rho nu is the energy density, and this one we are going to call as a proportionality constant B12. Why 12 means here the transition is occurring from ground state to the excited state. Ground state means first and excited state means 2, because here only we are considering the 2 levels only, and this B12 we are going to call as an Einstein quotient for stimulated absorption. This B12 we are going to call as an Einstein quotient for the stimulated absorption. So this is the first Einstein quotient. So how we are going to write? And R1 is equal to B12 N1 rho nu. Also we are also going to write like this. R rho 12 equal to B12 rho nu. We can also write like this also. Okay. So this is the first process. I will repeat again. So here we have 2 types of transitions. One is the upward transition and second one is the downward transition. So in upward transition, we have one quantum process. That quantum process we are going to call as an stimulated absorption. Whereas in downward transition, we have 2 quantum processes. One is the spontaneous emission and second one is the stimulated emission. So here we are going to consider the 2 energy levels, energy level system. So here the ground level and this is the excited level. So here E1 is the energy of the ground level and E2 is the energy of the excited level, and N1 is the number of photons in the ground level and N2 is the number of photons in the excited level, and rho nu is the energy density. And what is the absorption process means? It is going to be happen between 1 to 2, not 2 to 1, 1 to 2. So if some energy is incident on the atoms in the ground state, so some of the atoms absorb this energy. Some of the atoms absorb this energy and they started to move from ground state to the excited state. Okay. So that means here the rate of absorption is going to depend on, for example, we are going to consider R1 is the rate of the stimulated absorption. It is going to proportional. That means it is going to depends upon the number of atoms in ground state, first process, and also depends upon the energy density. So, and if you take off this proportionality constant, we are going to get a constant value. That constant we are going to represent B12. Why 12 means the transition is going to occur from first level to the second level, not second level to first level. That's why B1. This B12 we are going to call as Einstein quotient of absorption. Einstein quotient of the absorption. This is equation 1 we can call as. Okay. So next Einstein quotient. Next one is the, now you can observe that this is the upward transition. Now this is the upward transition. Next transition process is the downward transitions. In downward transitions, we have 2 types of emissions. One is the spontaneous emission and second one is the stimulated emission. First, we will go with the spontaneous emission. Okay. So, what is spontaneous emission? Already, as we know that spontaneous emission means already the atom is in the excited state. Already the atom is in the excited state. What is going to happen after the lifetime of the excited state? What is the lifetime of the excited state means? The lifetime of the excited state is 10 power minus 8 seconds. After the lifetime of the excited state, the atom spontaneously comes to the ground state. What is going to happen? The atom spontaneously comes to the ground state by emitting H nu energy spontaneously. So by emitting the H nu, this emitted photon is following the ordinary light properties. This emitted photon is following the, that means in ordinary light we have the spontaneous emission principle. That means it is non-coherent and it is not divergent and less intensity and brightness like that. So here, see here what is going to happen? The process is from second level to first level. Whereas in stimulated absorption, the process is from first level to second level. Whereas in spontaneous emission, the process is from second level to first level. That's why we are going to call as downward transitions. Downwards, same. Here N1 is the number of atoms in ground state and N2 is the number of atoms in the excited state. Now, the stimulated emission rate, the spontaneous emission rate, that means we are going to call as R2. The spontaneous emission rate R2 is going to depends on only number of atoms in the excited state. Where R2 is going to depends on number of atoms in the excited state. Here we are not giving any external energy. So that's why the rate of spontaneous emission is going to depends upon the number of atoms in the excited state. Whereas in earlier process, the rate of stimulated absorption is going to depends upon number of atoms in ground state. In the same way, it is also going to depends upon the energy density value. So here R2 equal to A21 then N2 by A21. 21 means we are getting the transition from second to 1. That means from excited to the ground level. That's why 21. Where A21 we are going to call as an Einstein quotient of spontaneous emission radiation. Where A21 we are going to call as Einstein quotient of spontaneous emission radiation. So this is one downward transition and we can go with the another downward transition rate. So the second downward transition is stimulated emission, which is the main principle involved in our laser, stimulated emission. So here what is going to happen? So after absorbing some energy, the atoms are in the excited state. Okay. What happens in spontaneous emission process after 10 power minus 8 seconds? After the lifetime of the excited state, the atoms come to the ground state by emitting one photon energy spontaneously without giving any external energy. Whereas here what is going to happen? So the atom is in the excited state. So now what we are doing? So now we are applying some energy to the atom in the excited state. Where we are applying? We are giving some additional energy, external energy to the atom in the excited state. So before the lifetime, so what we are doing? We are giving some energy to the atoms in the excited state. Now what it is going to do? So while emitting from excited state to ground state, the atom is going to emit 2 photons. How many photons it is going to emit? One atom, it is going to emit 2 photons. Why 2 photons? One is already the absorbed photon, another one is the additionally given photon. So that's why while emitting, the atom is going to emit 2 photons. These 2 photons are going to follow the properties of the laser. We have 4 properties of the laser. So these 4 properties are unique properties which are going to differ from the ordinary light. What are those properties? These 2 emitted photons are coherent. Coherent means they have same wavelength, frequency and constant phase difference. In the same way, these 2 emitted photons, they are having the monochromatic. That means they are having single wavelength, in high intensity and the brightness. So here also the transition is from 2 to 1, not 1 to 2, 2 to 1. This is also emission and the another earlier one is also emission, but there is a difference between these 2 processes. Earlier one, spontaneously the atom will come to the ground state by emitting 1 photon, whereas here if you see, so in At the in ground state, in excited state, we are giving additional energy. So by emitting, it is emitting 2 photons. By emitting, it is emitting 2 photons. And here the rate of stimulated absorption is going to depends on. It is going to depends on. It is going to depends on same number of atoms in the excited state. Number of atoms in the excited state. In the same way, here another factor is also going to be there. That factor is the energy density, because we are giving energy to the atoms in the excited state. So the rate of stimulated emission is going to depends upon the number of atoms in the excited state. In the same way, the energy density, because we are giving energy to the atoms in the excited state. That's why. So if you take off the proportionality, we have constant. That constant we are going to call as B21 and N2 rho nu. N2 is the number of atoms in excited state, rho is the energy density, and what is B21? B21 is called as the Einstein coefficient of the stimulated emission process. Okay, 2-1. Here also 2-1. That's why downward transition. So if you observed the three rates, I will write here the 3 rates. We can understand easily. 3 rates where R1 is the rate of stimulated absorption. Where R1 is the rate of stimulated, where R1 is the rate of. So R1 equal to B12 N1 rho nu. Okay. In the same way, R2 equal to A21 N2. Whereas R3, that means stimulated emission process, R3 equal to B21 N2 rho nu. Okay. If you observe the constants A and B, that means we are going to derive the relation between the A and B. We are going to derive the relation between the A and B. That means which is going to infer that we are going to derive the relation between the spontaneous emission process and the stimulated emission process. And here B21 and B12, these are the stimulated processes. One is absorption, that's why 1, 2, another one is the emission, that was 2, 1. Whereas here is A. So that's why this Einstein coefficients were also called as the relation between the A and B. So now, up to now, we just write the relations, how the rates, this 3 quantum processes rate. Okay, let's see the relation between these 3. How we are going to derive this relation. Let's see in the next slide. So next slide is, so how we are going to, the total probability of an atom from 2 to 1, total probability. So just we are writing total probability. Rho 21 equal to A21 plus B12 rho nu. Just total probability of downward transitions, total probability. As I said, these 3 processes we are going to get the probability values. So rho 21 equal to A21 plus B21 rho nu, because these factors. Okay. So now, what are the Einstein coefficient relations? What is the Einstein coefficient relation? How to relate these 3 quantum processes? So how we are relating? We are going to relate like this. Okay. B12 rho nu. This rho nu is the absorption. In the same way, A21 spontaneous emission plus B21 and stimulated absorption. This is stimulated emission and this is the stimulated absorption. This is the relation. From this relation, we are going to get the Einstein coefficients. So now let us start. Okay. So according to the Einstein, at thermal equilibrium, the downward transition equal to the upward transition. That means upward transition equal to down. R1 equal to R2 plus R3. R1 equal to R2 plus R3. And in another way, how we can write N1 rho 12 equal to probability value. N1 rho 12 equal to N2 rho 21. Here you can see rho 21. Okay. So rho 21 means this is the downward transition probability. Downward transition probability. Whereas upward transition probability is rho 12. Rho 12. Rho 12 means here rho 12 means B 1 to rho nu. This is the this is upward transition and this is the downward transition. I will write together here. Rho 1 to equal to B 1 to rho nu. This is the downward transition probability and this is the upward transition probability. According to the Einstein, what he is saying that at thermal equilibrium, the downward transition equal to the upward transition. And what is the relation means N1 rho 1 2 equal to N2 rho 2 1, where N1 is the number of atoms, because this is the ground state because this is absorption, whereas N2 is the number of atoms in the excited. This transition is from 2 to 1, whereas this transition is 1 to 2. That's why here N2 and here is N1. So finally, and in another way we can write here like this also. R1 equal to R2 plus R3. The downward transition means here R2 R3 and upward transition means the R1. So now we can continue the relation. So here N1 rho 1 2 equal to N2 rho 2 1. N1, what is rho 1 2 means? Here rho 1 2 means B1 2 rho nu, energy density. In the same way here N2 this one N2 A21 plus here, sorry, this one is 21 B21 of rho nu, energy density. So next step N1 B12 rho nu equal to N2 A21 plus N2 B21 rho nu. Okay, clear? Okay, clear. Okay, see here. Now what we will do? We will take rho terms one side. Okay, we will take rho terms one side. So then what we will get? See here. We will take rho nu terms one side. Okay, that means N1 B12 rho nu minus N2 B21 rho nu equal to N2 A21. Okay. So next step. What we will take here? Rho nu common. From this side, we are going to take rho nu as a common. Rho nu equal to rho nu common. We are going to take rho nu common. Rho nu N1 B12 minus N2 B21. That is equal to N2 A21. N2 A21. Okay. And next step. We are going to write equation in terms of the energy density, that is rho nu. So rho nu equal to N2 A21 divided by, what we are going to get? N2 divided by N1 divided by N1 B12 minus N2 B21. Okay, got it? Now we are taking the relation in terms of the energy density. Okay, so again we will simplify this relation. Okay, let's go. How we are going to simplify? So here we are going to rho nu, as we know that rho nu is equal to A21 N2 by B12 N1 minus B21 N2. Now we are going to divide numerator and denominator with the factor. Now we are going to divide the numerator and denominator with the factor. How we are going to divide? So we are going to divide B21 by N2. For both numerator and the denominator, we are going to divide with the factor B21 by N2. See how we will get this relation. So rho nu equal to A21 N2 by B21 N2. In the same way, denominator B12 N1 minus B21 N2. Okay, so B21 N2, B21 N2. So what is going to happen? In numerator N2 N2 cancel. Okay, in numerator N2 N2 cancel, whereas in denominator this whole term is going to be cancelled. So now what is the relation? Rho nu equal to A21 by B21, B12, B21, B12, B21, N1 by N2 minus 1. N1 by N2 minus 1. We get it this relation. Now, so this is the, again we are going to simplify. Again we will simplify. Okay. After simplifying only, we are going to get the A and B relation in terms of the A and B. Okay. So, what is the relation we are getting now? Rho nu equal to, energy density relation we are writing, equal to A21 by B21, B12, B21, N1, N2 minus 1. Here we need to remember that we are going to write two direct relations. That is, one is the Boltzmann constant relation and second one is the Planck's radiation law. Okay. So, with the help of this, we are going to simplify and we can derive our final relation. So, here with the help of the Boltzmann constant distribution law, directly we are writing. No need of going for the detailed relations. So, with the help of the Boltzmann constant distribution law, Boltzmann constant distribution, N1 by N2 equal to e power E2 minus E1 by KBT. N1 by N2. How we are going to write from the Maxwell-Boltzmann distribution law? N1 by N2 equal to e power E2 minus E1 by KBT. Where, and we can also write KBT. We can also write this, where N1 by N2 equal to E2 minus E1 equal to h nu by KBT, where h is the Planck's constant, nu is the frequency, kb is the Boltzmann constant, T is a temperature, because E2 minus E1 is equal to h nu or Ec, because we are giving the energy difference between the two energy levels. This one we are going to call as an energy gap. Okay. So, how we are going to write? N1 by N2, N1 by N2 equal to, as per the Maxwell-Boltzmann distribution law, N1 by N2 equal to e power h nu by KBT. The same we can substitute here. Okay. So, now the equation is going to become, rho nu equal to A21 by B21, A21 by B21, B12 by B21. Then what is this one? This one is here, e power h nu by KBT minus 1. This is the rho nu. We derived this one from our three quantum processes, three rates. One is absorption, second one is spontaneous emission, third one is the stimulated emission. So, we arrived. Okay. And another second one. So, now we are going to compare our energy density with the Planck's energy density values. Now, we are going to compare our energy density value with the Planck's energy density radiation. So, according to the Planck's radiation, rho nu equal to, according to the Planck's radiation law, the energy density rho nu equal to, this is also the direct relation we are writing here, the second direct relation. One is the Maxwell-Boltzmann distribution law and second one is the Planck's radiation law. According to the Planck's radiation law, the energy density rho nu is equal to 8 pi h nu cube by c cube into 1 by e power h nu by KBT minus 1. This is from the Planck's radiation law. From Planck's radiation law, the energy density can be given as 8 pi h nu cube by c cube into 1 by e power h nu by kBt minus 1. Okay. Now we will compare our energy density with Planck's energy radiation. Now we are going to compare our energy density with the Planck's energy density. So, how it is going to become? So, first we will write the Planck's energy density. 8 pi h nu cube by c cube into 1 by e power h nu by kBt minus 1. This is Planck. And what about ours? That is h nu rho nu equal to A21 by B21 divided by B12 B21 e power h nu by kBt minus 1. Okay, this is ours. So, check the equation. Check the equation. If any terms are going to be cancelled, check the equation. If any terms are cancelled, so how? So this one is going to be cancelled. What is going to be cancelled means this e power h nu into B21 is going to be cancelled. It is going to be cancelled. Now the equation becomes 8 pi h nu cube by c cube is equal to A21 by B21 by B12 by B21. Okay. So, if you are getting confusion, I will explain another step here. Easy way. So, before cancellation, I will explain one step. Okay. See here. So, B1 to B21. One is the upward transition, another one is the downward transition. So, B21 equal to B12. That means, so that's if you apply this one. So, the upward transition must be equal to the downward transition. Then, what is the equation? 8 pi h nu cube by c cube into 1 by e power h nu by k bt minus 1, that is equal to A21 by B21. Here 1 na, A21 by B21 means 1 only. Then we are going to get e power h nu by k bt minus 1. Okay, this one is cancelled. Now, what is the final equation? 8 pi h nu cube by c cube, that is equal to A21 by B21. That is equal to A21 by B21. Now we are getting the what we are getting? Spontaneous emission rate to the stimulated emission rate. 8 pi h nu cube by c cube. 8 pi h nu cube by c cube. So, see, what are the conclusions we are going to get from this one? A21 by B21 equal to 8 pi h nu cube by c cube. Here pi constant value, h constant value, c velocity of light constant value. That means the Einstein coefficient is going to be proportional to here if you see. So, what we are getting from here if you see A21 B21 equal to 8 pi h nu cube by c cube. Okay. All this is constant, this is constant, this is constant, this one. That means all these are the constants. So, that's why A21 by B21 is going to proportional to nu cube. That means it is going to depends upon the frequency. That means in turn it is going to depends upon the wavelength. That means it depends upon the emitted wavelength, emitted photon wavelength. These two are going to depends upon the emitted photons wavelength. So, that means see the conclusions. We will see the conclusion. So, here if you see, so B21 equal to the probability here A21 by B21 is proportional to the nu cube. That means the rate of spontaneous emission and the stimulated emission rate is going to depend upon the frequency. Now, to get a good lasing action, because for lasers we need to get a very nice laser process, laser action. Laser action, what is the condition we need to get lasing action means? Okay, if A21 by B21 less than 1, then only we will get the good lasing. That means instead of spontaneous emission, we need to get more stimulated emission process. Then only we'll get the good lasing action. Okay. So, and in turn, it is going to depends upon this spontaneous emission rate to the stimulated emission rate is going to depends upon the frequency of the emitting rate. If you see finally, what we are getting? We are getting the relation between the A and B only. A and B and also downward transition only. Okay. So, this is the Einstein coefficients. If you need, you can refer with the help of these links also. You can get the references. You can study. You can check it anything if you want.